Hello, this is Jack Jackson. In this section, we will perform a test of proportions, a hypothesis test, with the p-values being computed by using a binomial distribution. In our last video, we used a hypergeometric distribution to do the probability calculations for a test of proportions. And technically, that is the more correct way because most sampling is really done without replacement. So sampling done without replacement is realistic. A finite population is realistic, and that's when we would use a hypergeometric. But it has a disadvantage, and that is that the population size must be known. In a binomial, the sampling with replacement would produce a binomial situation. If the population is infinitely big, then the binomial is appropriate. If the population is not infinite but large, then the binomial is often a very good approximation of the hypergeometric, and so we can proceed using it. The advantage of the binomial is we do not need to know the population size. So if we know the population size and we're doing sampling without replacement, we should use hypergeometric. But if we don't know the population size, we're fine. We can still do test of proportions if we know, maybe we don't know the size of the population, but we at least know that it's big. And in that case, we can use a binomial distribution in place of a hypergeometric distribution to do our probabilities calculations. Now, let me just show you a few situations. This gives a side-by-side some calculations that I set up in Excel, and both of these have a population size of 40 and 15 successes in the population, so the probability of success on the first trial, and also the proportion of successes in the population is the same. But on the left, we have a hypergeometric distribution where sampling is done without replacement, and on the right, we have a binomial where sampling is done with replacement. We draw a sample of size 10. Now, population size is only 40. So there is a pretty significant difference in some probability values. So I've computed several different probability values there for comparison. And in particular, I'm looking at if we look at the number of successes in a sample and we want to do a left-tailed p-value, notice that the hypergeometric would return about 0.04 and the binomial would return about 0.06. So the binomial is not going to be good, and we would reach a different conclusion if, for example, we were using an alpha level of 0.05. Here are the two graphs from the previous time, and we can definitely see some differences in the shapes of those graphs. If we superimpose one upon the other, we get this graph here, and you can clearly see that the binomial is sticking out on the outer pieces, and the hypergeometric is taller in the middle pieces. So here's a little bigger sample size with our 160 where we do the same thing. Again, we're taking a sample of size 10. This time the probability of a success or the proportion of successes in the population is 0.1 or 10%. And let's say we look specifically at, we had come up with 3 successes in our sample of size 10, and we want a right-tailed p-value that corresponds to that. And here we computed that using a hypergeometric and a binomial. Notice they're very much closer together. The hypergeometric is 0.064. The binomial is 0.070. But still, there are some differences depending on what you put your alpha value. Maybe or maybe not, that would make a difference in your conclusion. The graphs are much closer together than they were for the previous example, but there's still some differences there. Maybe or maybe not enough to make a difference in your decision on your hypothesis test, depending on what the numbers come out to be. Now we're getting big enough that we can probably get by with using a binomial to approximate a hypergeometric. The population size is 1,200. We're doing a sample of size 50. And we're looking at the number of successes in the sample is 35, and we do a two-tailed p-value, and you can see those numbers in red at the bottom. The hypergeometric produced about 0.18, and the binomial is 0.19, and notice they're pretty close together, although really even they still don't agree to 2 significant digits. However, we probably could get by with this. The graphs are starting to look very much more alike here. So all of that was just to show you that there are some differences in these, and the differences are significant if the population size is small. Okay, so let's look at this example. Suppose that it's claimed that 80% of all U.S. citizens support a particular bill. We take a random sample of 90 citizens and find that 70% of them support the bill. Do we have sufficient evidence to suggest that the true proportion of citizens supporting the bill is less than claimed? Use alpha equals 0.05. Now, since sampling is done without replacement, technically this is a hypergeometric distribution leading to a distribution of proportions. But the population size is unknown, so we can't use a hypergeometric distribution. However, the population size is very large, all U.S. citizens. That's extremely big. So we can assume that the probability of success each time is nearly the same. So a binomial distribution is practically identical to a hypergeometric distribution in this case. So we will proceed using a binomial distribution. The null hypothesis is that the population proportion is what they claimed. P naught is 0.8. The alternative hypothesis is that P naught is less than 0.8. So since it says less than right here, we use a less than here, which means this is a left-tailed test. So all of the p-value is to the left. So the observed proportion, p hat, is 0.7, so we need to find the corresponding x to that. 0.7 is the percentage of successes in the sample. The sample size is 90, so 0.7 times 90 is 63. Remember, that has to be a whole number. So the p-value then is just the probability of getting that 63 or something more extreme. In this case, since it's a left-tailed test, more extreme is further to the left. So we're finding the probability that x is less than or equal to 63 from a binomial distribution where n is 90 and p is 0.8. So we just do that here. You can see it over here on the right in the TI-84 screen. Binomial CDF 90.86, and we get about approximately 0.016. If you were doing this on a TI Inspire, instead of giving it just 63 at the end, you would give it 0 and then 63 because it does their CDFs as lower and upper. Whereas a binomial with discrete CDFs on the TI-83 or 84, always you just give it the upper, and the lower is always 0, or always however far it will go to the left. So anyway, we get a p-value from our binomial distribution of 0.016. Notice that's less than 0.05, which is our alpha. So there is enough evidence to suggest that less than 80% of the citizens support the bill. So someone is claiming a little more support than there actually is. We're not going to call them a liar unless we have evidence to support that, and we do. That 0.0156 corresponds to this shaded left tail here. Let's try another example. In the Journal of Global Business, spring 2002, it's reported that 64 of 106 U.S. shoppers reported the term "made in the USA" means that 100% of the labor and materials are from the United States. A claim is made that 70% of all U.S. shoppers have the same interpretation. Does the reported study produce sufficient evidence to suggest that the true proportion of U.S. shoppers is different than claimed? Use alpha 0.05. Well, again, the population size is extremely large and unknown, so we'll use a binomial distribution appropriately, even though the sampling was likely done without replacement. So we're using a binomial to approximate a hypergeometric here. The null hypothesis is that the true proportion, P naught, is 0.7. The alternative is that is not equal to. Notice it says different than, so that's a not equal to or two-tailed test. The observed sample, n, is the sample size of 106, and x equals 64, is the number of successes in the sample. 64 divided by 106, or about 60%, is the p hat. So we got a sample proportion of about 60% when they claim it should be 70%. So we're going to do that with the two-tailed test. Since 60% is to the left of or less than 70%, we'll find the probability that x is less than or equal to 64 and then double it to get our p-value. And this is from a binomial distribution with n is 106 and p is 0.7. So we can do that with a binomial CDF, 106 in the probability of success p is 0.7, the x value is 64, but then we got to double it because it's a two-tailed test. And we get, after we double it, it's 0.04355, so about 0.044, and that, then you need to compare that to alpha. We're using an alpha 0.05. 0.044 is less than 0.05, so we say that there is enough evidence to say that the true proportion of shoppers with this opinion is different than 70%. If we wanted to illustrate this probability, we're talking about the area of these two things here. Here I actually computed those bars, added up those probabilities. They're not 100% symmetric, but they do add up again to about 0.04 at least. Example 6. Suppose that a statistics department claims that 95% of the students who do all of the assigned homework will pass probability in statistics 1 with a grade of C or better. A sample of 20 students who did all of the homework for this class was taken. It was found that 16 of them earned a C or better in the class. Does the data give enough evidence to support the claim that the department is overestimating this proportion at the alpha equals 0.05 level? See if you can do this one yourself. Press pause. Come back when you've got it done. Well, sampling is done without replacement, indicating a hypergeometric distribution. However, the population is quite large and is unknown, so a binomial distribution is appropriate. We really don't have an option for a hypergeometric because we weren't told the population size. The null hypothesis is that the true proportion is p0 is 0.95 as they claimed. The alternative hypothesis is that p0 is less than 0.9 because we are seeing if they're overestimating. So we want to see if they're saying it's too high, then we're saying the alternative would be that the proportion is too low, is lower than 0.95. So it's a left-tailed test. The observed data, we have a sample size is 20, and we had 16 successes there, which is a proportion of 0.8 from the sample. So we're finding the probability that x is less than or equal to 16 from a binomial distribution where n is 20 and p is 0.95. Here it is worked out on a calculator, all the probabilities to the left. So we have a whole bunch of really short bars that we can't see from 0 up to say 14, and then 15 and 16 are big enough we can see those. And we add up all those areas and all those heights. Since the widths are 1, they're adding up all those areas. And we get a binomial CDF to do that, and we get a p-value of 0.0159, or approximately 0.016. That's less than 0.05, which is alpha. So we reject the null hypothesis. So we would say that with a p-value of 0.016, there is enough evidence to say that the true proportion of passing students is less than the 0.95 at the statistically significant level. So that gives you some examples of testing a hypothesis using a binomial distribution.